think we are recording, and I am just going to apologize. I don't have an awesome studio like Mr. Boone, so the sound quality is not going to be awesome, but hopefully you can at least get out of what we need to get out of today. Okay, so today what we're going to look at is derivation for the moment of inertia for a cylinder, and the axis of rotation for that cylinder is going to be through that center. So you can see that blue line there as our axis of rotation for our cylinder. Remember, take a moment and pause the video right now and remind yourself exactly what a moment of inertia, also called rotational inertia, really is. Recall that that moment of inertia is simply the adding up of all of those little bits. So let's take a little bit of time and label your diagram that you have in front of you. So the radius is already labeled for you as well as the length. But what I want to do is I want to work on the inside here. So maybe we'll work right here, right? And that radius there will be, let's say I'm looking at, I love how my smartboard is not lined up with what I want it to do. Okay, so let's look at this little mass bit right here. So that little mass bit is called a dm, right? That's an infinitesimally small mass bit. And then we have our little r radius. So notice those capital and those lowercase are actually important. So that little mass bit, that dm, is located at some distance from the axis of rotation, and that's the little r. The total radius of the whole thing is a capital R. Also, the total mass of this whole thing is capital M. All right, so if we look at a moment of inertia in a little bit more of a simplified version, a moment of inertia is just our mass times our radius squared. So this is for a single object. So this is what would be true for this little mass bit that we have put up, drawn on our diagram. Now, what we really have to do, though, is we have lots of those little mass bits, so we have to add them up, right? So that's where that sigma comes from in the statement. Now, if we have individual small particles, or like little mass bits, we can just add those up. But if we have a continuous body, meaning like a solid object, we're going to have to integrate. So remember, just kind of think through in our mind, what does integrate mean? It means to add up, right? Think integrate, think add up. So let's take a look for a moment at this moment of inertia equation in the box. So notice a couple of things. We have that integral sign telling us to add up. Notice we have the function r squared, right? Because that moment of inertia is dependent upon the distance from the axis of rotation out to that mass point that is squared. And then we have the dm. So those were those little bitty mass bits that I drew over on the diagram that we were talking about in a little bit. Okay, but here is the problem with this particular statement, and this is where the geometry of the situation, which we're going to be talking about, is going to dictate how you solve this problem or do this derivation. Okay, so the problem that we need to identify is that this variable right here, so that r is the variable, does not match that differential, that dm, those little mass bits. And so we can't just use this integral as stated. We've got to do some stuff to it in order to be able to actually integrate the function, because radius is not in terms of mass. So what we really have to answer is, how does the mass vary with radius? So what I'd like you to do right now is I'd like you to pause your video, and I would like you to write out two things. I would like you to write out the formula for density of a solid object, and the second thing I'd like you to do is find out what is the volume for a cylinder. So equation for the volume of the cylinder, and then also an equation for the density of an object. Okay, we are back. And I asked you to write out two things. So density, we are going to use the lowercase Greek letter rho. Some of you use a capital D, but I'm going to use that lowercase rho. And then that is going to be equal to our mass divided by our volume. And then I also asked you to find a volume for our cylinder. So if we take a look at our volume for our whole cylinder, that would be pi r squared times right? So that's just that base, this circular base, right, times our length there. Okay, and so what we're going to end up doing is we're going to substitute in for our volume, and we are going to solve for mass, because remember right now our goal is to figure out how mass varies with radius. So we really have to combine these two statements, knowing that our cylinder has a uniform density, right? Our cylinder has a uniform density. We aren't able to do this for something that isn't uniform in terms of density. We would have to have some sort of computer program to help us with that. Okay, so if we take a moment and I want you to substitute this statement in for our volume and then solve for mass. So go ahead and pause the video and do that. And now you're back, and it should look like this. All right, here we go. Sorry. All right. So we have our density rho times pi r times L. R squared times L. And then what we're going to do is, if you think about mass varying with radius, doesn't that just say to you dm dr, right? That should say to you dm dr. We want to know how the mass varies with radius. So what we're going to do is we're going to go ahead and take the derivative of this mass function with respect to r. You're good at that, so go ahead and take that derivative of that function, dm dr. And that'll just be 2 rho pi f. You with me? Oh, I forgot my r. Where'd my r go? Help me find my r. So rho 2 pi r times L. And I know I'm going to blow Spencer's wig back right now, but we are going to multiply both sides by dr. Hold on, Spencer, you can do it. All right. So now this is dm is going to be equal to rho 2 pi r L dr. Okay. So why did we do all of this? We did all of this algebra and a little bit of calculus to be able to substitute in right here. So if we take a look at what we just figured out, we figured out how the mass varies with the radius. So if we take this statement and substitute it in our equation for dm right up here, then our variables will now match, right? So we'll have an integral with respect to r, and we can actually figure out what that is. All right, so what we're going to do is we are now going to substitute that back in. So we're going to substitute in rho 2 pi little r times big L dr up for the dm, right? We're just going to substitute that in. So go ahead and do that, rewrite that, and I'll meet you back in just a moment. Okay, so we're back, and I want to make sure I'm just super uber duper clear. We are going to notice that this dm right here, that little bitty mass bit, is going to end up being substituted up here, right? And we have rewritten our moment of inertia in terms of dm. So if I scroll down here, you can see that that is done. Now I want you to notice a couple things. Remember, when we started this, we had a problem. We had our variable, so our radius is what's varying here, and it didn't match this differential out here on this side, because we were trying to add up radius in terms of mass, and those two variables always have to match when you're integrating, because you're integrating the function with respect to that variable r, not m. So we had to go through and rearrange and do some work with our volume and our radius to figure out how those two related. So how did the mass vary with radius, right? Because obviously, as you get further and further out, there's more and more mass that's going to be there, right? Okay, so if you look at our highlighted statement, all of our things that are variables, things that can change, are all now in terms of r, right? Because our density here is going to be constant, 2 pi is constant, and then L is just that length of that cylinder, and that isn't changing since our axis of rotation is through the center of that. Okay, so now really is the easy part. The rest of this is we're going to just integrate. But we do have to state what our variables are going to be, meaning not our variables, excuse me, but our limits of integration. All right, so if we look back up at our picture for just a moment, you're going to notice that we need to go all the way from the inside here all the way to the outside of that radius. So our limits of integration are going to be from 0 to a capital R, because we're going to add up all the mass bits all the way from the axis of rotation out to the outer edge, which is at R. So what we're going to do now is we're just going to simplify the statement a little bit and put in our limits of integration. So our limits of our integration, again, are going to be all the way from the 0 right at the axis of rotation to the capital R, all the way out to the side. And then we are going to pull out, or we're going to just kind of combine our two r's together. So we've got r cubed, right? So we've got r cubed, and then we will have all of our constants, right? So we'll have 2 pi rho L, those are all constants, times dr, right? Times dr. So just speaking to make things a little bit simpler, we can take all of our constants and pull them out in front of the integral because they are just constants. They aren't going to change or vary. So we're going to pull those out. So 2 pi rho L, again, our limits of integration are 0 to r, and then we're going to integrate the function r cubed. All right, so this one's a pretty straightforward one. It's just like a polynomial. We're going to power that up, right? We're going to power that up. So we are going to keep our constants out front. And we will have r to the 4th, right? So we add 1, but we got to divide that by 4, because we know that when we take the derivative of r to the 4th over 4, we have to have that that derivative be r cubed, right? And then we are going to evaluate that function, from 0 to a capital R. That's where our limits of integration come in, right? That's where our limits of integration come in. And so when we do that, we will end up with our moment of inertia is 2 pi rho L, and then, because this is just like, put this in parentheses, right, that's just our constants out front, here are constants out front, and then this will be capital R now. So notice that this little r is what varies. It varies from 0 up to a capital R, so we're going to substitute in our values. We've got r there. So this would be r to the 4th over 4 minus 0. All right, so if we substitute in 0, remember, change in anything is always minus initial. So we take our final, which was our capital R, minus our initial. And then the hard work is really done. The rest is just some simplification. And I want to just pause for a moment, and I want you to look at what our goal is. Remember, our goal is, whoops, sorry friends, let me get rid of that. This is our goal right here. And so we're like, well, where does that come in? How does that work? We're going to have to do some substituting back in, but it's not hard. We can do that. Right? We can do that. Okay. Sorry again. All right, so we take a look at this. We simplify down a little bit, and we've got our moment of inertia is equal to, and then we'll go, we've got our 2 here, we'll cancel out with this and leave that as 2. So we've got pi rho L r to the 4th, over 2, right? Over 2. All right, to finish this whole thing out, we are going to want to write our moment of inertia in terms of m and r, and we're going to want to get rid of our density our row here. So we want to simplify that back down. So if you remember from above, that we wrote our mass in terms of our density, but notice we use this little r here, right? Because that was what was going to change when we looked at our little different mass bits. So what we're going to do now is we're going to actually use the density for the whole cylinder, the whole big chunk together, right? And if we think through that, that density will just be our mass, our total mass, which is a capital M. So notice I'm using a capital to represent the mass of the whole thing, not just our little bitty masses. And then that will be pi r squared times capital L. All right, remember, so the r is the whole volume of the whole big cylinder. That radius is the whole thing. So this is the density for the whole thing. The only reason why this works is that density is uniform, right? So the density of just a little bit of it is the same as the density of the whole thing. So we're going to take that and we're going to substitute it back in, and then you're going to do some Kung Fu algebra to simplify. So I'm going to ask you right now to pause the video. You are going to substitute that in for this row right there, and then simplify. All right, so I've shown my substitution here. We've got a complex fraction, but luckily some of our stuff cancels out, which is really what we want it to do. So we're going to notice a couple of things cancel. We're going to notice our pi's cancel. We're going to notice our capital L's cancel. We're also going to notice that a couple of our r's cancel as well. So this will leave us with I is equal to, and then this will be capital M r squared over 2. Woo! We did it! Yay! We ended up with our mass of our whole cylinder times the radius of our whole cylinder squared divided by 2, or 1/2 mr squared. Okay, so I'm going to go through and just recap very briefly what we did. So we started back up here, and we recognized that we had to do something with our mass in order to get our variables to match. And so we used the uniform density to do that. And remember, our goal is to end up with our moment of inertia as being 1/2 mr squared, capital M. And in this guy, we could actually make this capital R squared, right? That's where we wanted to end up, not our little r, capital R. So correct that for me if you would. Okay, so we come back and we recognize and we use our density formula. We take our density for our cylinder and rewrite it in terms of little m and little r, and we took the derivative of it. And we took the derivative of it so that we could figure out how mass does indeed vary with radius. That's what dm/dr really means. How does the mass vary with radius? And so when we solve for our dm, then we can substitute that back into our integral. And in substituting that statement down there back in with our integral, that allows us our variables to match. And then we can actually perform the integration, right? And so then when we come down here and we do our integration, we substitute it in for our dm, and we get all of our variables to match. We simplified, we pulled our constants out front, and then we integrated with r cubed with respect to r. And we used our limits from 0 to capital R because, again, we're looking from our axis of rotation out to our outside. And then once we did that integration, we ended up with a function that was had something to do with r to the 4th power, and we're like, this is not where we wanted to go. What's up with that? And then we needed to recognize that we needed to use our density for the whole cylinder and substitute back into our integration, or substitute back into our moment of inertia, and then simplify. A couple of things that I would ask that you do right now is I'd like you to go to page 255 in your textbook. There's a sample problem 10-7 that does the same operation but for a different geometry. And I want you to look very carefully at that, and when you are, you want to answer and think about the questions like how how does their derivation of the moment of inertia for a uniform rod with the axis of rotation through the middle of that rod, how does that derivation look similar to the one we just did, and how is it different? So like, how does the general method of what we're doing stay the same, but how does it look very different for the different geometries that we are going to use? Hope this was helpful. Ask me any questions when you get back to class on Monday. Thanks for watching.